Okay, sorry, my mic was off. Um, I'm going to repeat once more. So we when we were talking about division, we said that there are three equations to solve here. One of them is an equation, another an equality, another is again about signs. So if we take care of these three, we are going to get just a single answer for that division, and this answer would be such that it's going to have the same magnitude for any of these options. So you can change the sign of dividend divisor without changing their magnitude. You're going to see that the quotient and the remainder has have the same magnitude in all these cases. So this is going to be the same over here. You're always going to get a 4 and a 2, a 4 and a 2, right? So you always get a 4 and a 2 as a quotient and 2 as a remainder in all of these cases, if you consider that the sign of remainder matches the sign of dividend, right? Now, the problem here is since we are doing that through an equation, and when you're talking about doing different steps, and in one of that step you get a different answer, you might land up with this answer -5 and 1, which is a wrong answer, but it satisfies everything except the last third equation. Sine of s should be sine of equivalent to sine of dividend. So all of these other equations are solving in this case. So this answer needs a correction. Now this is not a wrong answer. This is something like that you have you have to take say 4 steps, and after taking those 4 steps you landed up with this answer. So this is the last step, and you had this answer, and this needs a little correction, right? So when you're talking about signed numbers, there are going to be some cases where you land up in a different answer. So instead of having a minus,
Sir, if divisor is negative, then what will be impact?
the same thing, it doesn't matter if devices. So I'm going to take if you want, I'm going to take that first as well. So let's go back to our case here where divisor is negative. So in these two cases, the divisor is negative. So I'm going to rub this here, and we are going to do this, right? So rub this here as well. Let's do this. So if I go with say something like 4, so I'm going 3 into 4 is will be -12, right? So -12 in that case, but I have to do a subtraction as well, so that would become positive, and this positive, so it's would be the highest answer. So I'm going to go for -4 in this case. So -3 into -4 will be +12, which is after subtraction is going to give me 2, right? Uh, since I have reached the same sign, so I have got the divisor's dividend sign equivalent to the remainder sign. This is my right answer. In this case as well, if I'm going to have -3 over here and I have 4 over here, so -3 into 4 will be -12, and since it's a negative over here, so this would be -2, and since this has got the same sign as this, so this is also the right answer. We did this as well.
So this means we decide quotient sign minus or negative on the basis of uh, you can say
Divisor.
divisor.
Yes, yes. The sign of quotient is going to change on the sign of divisor. So if the divisor is negative, uh, then your dividend, sorry, your quotient is can be negative or can be positive. It
No, I
depends
mean
on
that it depend on the dividend.
divisor and dividend both, right?
Okay.
So you are dividing it the divisor with the dividend. You are dividing the dividend with the divisor. So they both signs are going to matter the sign of quotient. But the important rule is that the remainder sign should always match the sign of dividend.
So we just have to make sure that the sign of the remainder matches with the sign of the divisor, and if
Yes.
it doesn't matches, then we'll change the sign of the quotient.
Not the quotient. You're going to see that if it doesn't match, you need a correction step, and that correction step is normally just to change the sign of remainder, not the quotient, right? And that just adds or subtracts one digit from the quotient, one number from the quotient. It either adds a number or it subtracts a number, that in the correction step. So quotient sign doesn't really changes but the remainder sign changes, because if you have to go for the third equation where you say that sign of remainder should match the sign. So in our if we landed if we landed up in this answer, so let's do this thing. If instead of doing it with -3, if instead of obtaining a -4 and 2, um, sorry, um, what was that? We were doing a 14 and 3, -14 and 3. So we had a -4 over here and -12 over here, which was giving us -2, right? So instead of having this answer, if we obtain an answer like this, where we also satisfy the first two conditions, where, for example, we have -5 over here, and we get a -15 over here, and a +1 over here at the end, right? So in this case here, you're going to see that if after taking the required set, you might come up with this answer, and this is quite possible. This is quite possible, but in this case, in all these sign division algorithms, it can happen that you end up with this answer, and in this case, you just need a correction, and that correction resolves by making the sign of remainder equivalent to the sign of uh, the dividend. And this means that this one should be actually this remainder should be actually negative, right? How can we make negative? So because the remainder and the divisor here 3, right?
So,
So
so in simple, that the uh, the quotient and the uh, divide and sign should not be same. It should be different. Otherwise, remainder will be on the higher end.
the quotient and what? The quotient sign and
Quotient sign and the dividend.
this sign here. No, it can be same as well. Like this. In this case, they are both negative.
No, no, sir. I'm talking about -14 and -15. That this -14 and -15 should not be same. Okay, 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 okay. Sorry, sorry, sorry.
It's not about actually divide subtracting with -15 or -12. What I'm trying to say is
You mean that it should be different, not same?
no. It in different cases it's going to be it's going to be different, because yeah, it's go you should be it should be different, because you're at the end you're doing a subtraction operation. So
Yes,
if you're subtracting with the same signs, then this means that the result would be a little. If
higher
you're
end.
subtracting with the different signs, then the result would be different, right? So it's going to be adding both of them. So their signs should be same in this case, na? So it's because there is a subtraction operation happening over here. So their signs are always going to be same. So in this case, like we did over here when we were talking about all these operations. So if this is positive, this should be positive, and if this is negative, this should be negative. This is positive, this should be positive, because of this operation, negative operation, the subtraction operation. So their signs should be same, right? So that's one thing, but that's a normal process. That what I was talking about was you can land up with this answer, but this needs correction, and the only correction you need is you need to change the sign of the remainder so that it matches the sign of the dividend. Now, in order to change the sign of the dividend, the sign of the remainder, what you can do is either add this value or subtract this value. So if I add 3 to it, it's still going to be positive. If I subtract 3 from it, this is going to be a negative answer, right? So I'm going to get the same negative answer as my dividend. So I need to subtract 3. And when I'm subtracting 3, then I need to adjust my quotient by adding 1 to it. I'm going to come to the correction steps, but if I do this correction step, that is, if I subtract 3 from my remainder, and when I'm going to subtract 3, I'm going to add 1 more to the quotient, because this is why I'm subtracting 3 from it. So then you're going to see that this thing changes to this, because if I'm going to subtract 3 from it, it's going to be -2, and if I add 1 to this, it's going to get -4. So I'm going to land up with the correct answer now. So in division algorithms, what happen is you write the steps that it's going to take, and it might land up in this case. So at the end, what you check.
Why did you put +5 here?
Let me just complete. I'm going to come to the questions. So when we come to the final answer and we say that this sign is not matching, then we do go for a correction step. In a correction step, we either add the remainder, the dividend, sorry, the divisor. We either add the divisor to the remainder or subtract the divisor from the remainder to make it with the matching sign. So this matching sign can only happen if you subtract the divisor from the remainder, and then if we subtract it, we add 1 more to the quotient, right? And if we add it, then we subtract 1 more from the quotient. I'm going to come to the correction step, but if you do this, then you are going to get the right answer. So doing all this and getting this answer does not mean that you have done it wrong. You just need 1 correction step at the end, and that's going to make your answer correct, right? So in division algorithm, what's going to happen is we are going to go with some algorithm, and at the end, what we are going to do is we are going to check the signs of the remainder and the sign of the dividend. If they are matching, that's fine. You don't need any correction step. But if they are not matching, then you might need a single correction step, which is either to just add or subtract the value of divisor from the remainder, and likewise add 1 or subtract 1 from the quotient, right? So that's going to make your answer correct. And this is what happens. That's an additional correction step you might need in some cases. So I'm going to come to the algorithm now. First, your question, Ms. Sirina.
So I was asking that why didn't we multiply it with +5? Then the remainder could have been negative -29. That could have satisfied the condition as well.
No, how is -29 going to satisfy it? Because 29 is quite bigger than 3. The condition remains the same, that the 3 should always be greater. The remainder should always be less than the divisor, the magnitude of the remainder, right?
And the previous two conditions.
We have 3 conditions now. We have not 2, we have 3 conditions. All these 3 should be satisfying. The first one is the basic condition, which is an equation. The second is an inequality, which was previously just taking the magnitude. When we were talking about positive numbers, we were just checking that this number is less than that. But now we are going to take the magnitude of that number. So even though it has got a negative sign, you can say that 3 is less than -29. But if you're talking about the magnitude of -29, that's bigger than 3. So we are always going to go for the magnitude. And the third thing is the sign should be matching, right? So if we take care of this, then we are always going to get the right answer, right? Okay, so now I'm going to formally come to my algorithm for the signed numbers, right? Now we are going to go with a non-restaurant division. Okay, and in this case, since we need a correction step, so we are not really going to be deciding the quotient bits as zeros and one. Rather, we are going to take one more digit, which is a -1. So so whenever we are going to do a subtraction, which is going to be our normal operation. So in division, subtraction is our normal operation. So whenever we are going to do subtraction, we are going to put a 1. Whenever we are going to do an addition in our steps, we are going to put a -1. So at the end, we are going to come up with just quotient bits as 1 and -1s, and then we need to then convert it into binary form. And then at the end, we are going to look at the hardware circuit for that as well. Okay, so the easiest thing that we can do in trying to find out whether we need a -1 or 1 is check to the sign of divisor and the sign of remainder. So if they both are same, then the q bit or the quotient bit is 1, and we are going to do subtraction, else we are going to do an addition operation. Okay, so this is the simplest thing that we have to check whether we can do subtraction or we need to do addition. Okay, so I'm going to go with my first algorithm on sign division. Rather, we are going to just have this only algorithm for sign division. There is another algorithm which is the SRT algorithm. It's also, you can do it yourself. It's not very difficult, but the thing is that still in SRT you need a correction at the end. So in all these sign division algorithms, the last step needs a correction. And that is why division is a lengthy process even for the latest Intel processors as well. It takes a lot of time, and not only a lot of time, but it cannot be pipelined as well. So you cannot divide that into stages and do that similar to the array multiplier that we did in the last lecture. So division is a complex operation and it takes a lot of time. So when you're talking about sign division, in any algorithm of sign division, you need a correction step at the end. You might need that. Okay, so let's look at this algorithm. We are going to start with a dividend. So this is our dividend. Remember, we are talking about sign number. So this is a positive number because it has got MSB 0. So we are talking about 8 bits. So this means that divisor should come in 4 bits. So the 4-bit divisor is 1001, right? But since this is a sign number, so this means that we are talking about this is not actually 9. 1001 is not actually 9 because this is a sign number. So this gets a value of -8 plus 1, that is -7, right? So this is actually -7 that we are talking about in this case, right? So it's a negative number that we are going to divide, and this is a positive number. So I'm not calculating what that value is. We need to find the answer. Then we are going to check what that value is. Okay, so -7 will have its 2's complement as 7. So we have written that as well in 5 bits. We could have written that in 4 bits as well, but 5 bits means that this extra sign bit is going to help us in our calculations, because this is going to ensure we get the right signs at every step. If you don't add this, you can still get your answer, but in these subsequent steps you might get it a little difficult to maintain the sign, and sometimes your answer gets incorrect. So it's better if you add one more bit to it, and your adder should be of 5 bits, so that makes the thing everything very easy to handle. So we are talking about an adder of 5 bits, right? Okay, so the first step, again the same thing, that we are going to take this dividend and copy it as it is in the partial remainder. So the partial remainder is actually 2k bit plus 1 for sign. So it's a 2k plus 1 bit register, and these higher bits are basically going to be going to the adder, not the lower one. Okay, the first step is to shift it left. So we are going to shift it left, and once we are going to shift it left, now the steps are a little different, right? So when you're talking about sign numbers, so what we need to check is whether we can do a subtraction or we need to do an addition, right? So we cannot do subtraction all these steps. So how do we check this? So we check that the sign of this partial remainder is equal to the sign of the divisor. So divisor is negative, right? So divisor is negative and it's going to remain the same in all these steps. But the sign of the partial remainders are going to change in every step. But so divisor is negative, but the first partial remainder that we obtain has a positive sign. Now, if they both signs are not matching, this means you do have to do addition, right? And you have to put the quotient bit as -1. I'm going to come later in hardware how we're going to represent -1. So we are going to actually not really store -1. This is going to be converted on the fly. So let me just complete this, and then we are going to come to the hardware part as well. How is this going to be implemented on hardware? So we are going to set quotient bit as -1. This is on paper. We are going to set it as -1 because in after we have done all of them, we are going to convert that in its actually binary form. So in this algorithm, what we are going to get is quotient bit is either -1 or 1, right? And then we are going to convert that into binary form. Any question here?
Yeah, sir, just a clarification required. The condition says that the sign of S0, it is a non-shifted state.
Uh-huh.
So the left, the most significant bit, MSB, would it be the one which is in the actual question, or would it be the extra bit that we had added?
Actually, when we're talking about the signs of S and shifted S, so basically this is when we're talking about this bit, this extra bit, this is something that we have put it ourselves, right? When you're talking about k bits, it was 4. K was 4 over here. So all these numbers are of 4 bits, and we have to represent any number which can be stored in 4 bits, right? This extra bit was what we have put for our clarity, and we have done that so that our addition steps are more clear whenever we are going to the next step. But you can do that without that bit as well, right? So this is just an extra bit. Now, when we are talking about this extra bit, this is actually the same bit as the MSB in the first time, right? And when you're going to shift it left, that's going to be the same bit which is going to be shifted over here. Okay. So when you're talking about S naught or 2S naught, they are going to be actually the same thing. Okay.
Okay, sir. Thank you.
Right. So in every step, you can see here that they are going to be the same. So if it's 1, then 2S1 is also 1, and this is 0, this is also 0. So this is going to be the same. Okay. Thanks for pointing this out, because if you are getting any difficulty here, it's good to ask the question. But the thing is that if you take the sign of S naught or 2S naught or shifted one, that's going to be the same sign. But why we have written S naught over here is because in this second step, this is actually the same sign. In the second step, we need to do the addition or subtraction operation. So we need to find out what we have to do over here. So we have shifted it. We have seen that the sign is actually opposite. So we have a 0 over here and a 1 over here. So a positive and negative. So this means that their signs are not matching. So we are going to put the quotient bit as -1 and do an addition. So addition means we are going to add this number. Subtraction means we have to add this number, right? So we did an addition. So 1 0 1 1 1, right? And then we are going to shift left again. The signs are matching now, 1 and 1. So we are going to do a try subtraction. So try subtraction means to add this number and put the quotient bit as 1. So we are going to put the quotient bit as 1 and do a subtraction, and then in subtraction we are actually adding the 2's complement value. So 1 0 1 1 0 1 0 1 0 1, and ignore the carry out from that. And so we get this number. Shift left. The signs are not matching, positive and negative. So we do the same thing that we did in the first step, put the quotient bit as -1 and do an addition, which is to add the divisor actually itself. And then we have got a -1. So a negative means that in the next step we are going to do a subtraction, put the quotient bit as 1, right? So we are going to do as many steps as there are bits in the divisor. So there are 4 bits in the divisor. So we are going to do 4 steps: 1 2 3 4, and finally we are going to do we are going to get a number which has got a negative answer. Our dividend had a positive answer. So this means we need to have a correction at the last step. So, but we are going to come to that later. So this is the divisor. This is the remainder that we have obtained. It's a negative remainder. We should have obtained a positive remainder because the dividend was positive. So we are going to come to that. So the quotient that we obtained are -1 1 -1 1, right? So these are two things that we have obtained here. -1 1 -1 1, that's a quotient, and the remainder is actually a negative answer. So we need a correction step in this case. So I'm going to come to the correction step. So we after that we need a correction step. So I've chosen this example because there is a correction step involved over here. Now a correction step is simple. In a correction step, what you do is either you add the divisor or you subtract the divisor, right? And if you are going to add the divisor, you are going to subtract the quotient one. You are going to just subtract one from the quotient. If you're going to add the divisor, you're going to if you're going to subtract the divisor, then you're going to add it, and if you're going to add it, you're going to subtract it, right? So in the final remainder, since s has opposite sign, so we need a correction. So if then we have to look at what is the sign of s and the sign of the divisor. So divisor was negative in our example. The sign of remainder was also negative. So if they both are same, now if they both are same, how can you change the sign of remainder? So you need to subtract it, right? Otherwise you cannot change. So if they both are positive and you want to make this as negative, if you want to make the remainder negative and both of them are coming as positive, how can you do that? You need to then subtract that value from that remainder, and then it's going to be negative, right? Subtraction means you add minus d, right? And once you do a subtraction, what you do is you increment q. Okay, so if their signs are not matching, so how can you change the sign of remainder in that case? If this is positive and this is negative, and their sign is not matching, this means this is positive, this is negative, and you need to make this as negative. So what you can do is you add this value to it so that it becomes negative, right? So this is a very simple step, and this is the same thing that we were doing over here as well. If you look over here, we did the same thing as well over here. So if we landed in this case where we have a positive thing over here, but we should have got a negative one. Now if this is positive and this is positive, how can you make it negative? How can you make this remainder negative? You have to subtract this divisor, right? Otherwise you cannot add it. If you're going to add it, it's still going to remain positive. So the only way you can make it negative, if they both have the same sign, then the only thing that you can do is you can subtract this value from it, and then it's going to get a negative answer, right? And when you're going to subtract it, you're going to add 1 to the quotient value, right? And then you get the right answer. So the same thing is happening over here, that if the signs are same, you're going to subtract and add, and if their signs are different, you're going to add and decrement. Okay, so in this case, in the previous case, what we had was the remainder was negative and the divisor was also negative. So their signs are matching. So if they are matching, you are going to subtract this value from this. Subtraction means you add the 2's complement to it. So you add the 2's complement to it, and then you get 0 0 1 0 1. So this is what you did: 1 0 1 1 1, and forget about the carry out from this point. So this is now positive, and this is also positive. So you got your positive remainder, and this is what you wanted. So since you have done a subtraction over here, right? Since you have done a subtraction over here, you need to add one more to this value, the quotient value, right? But up till now we don't know what this quotient is. It's basically a number in ones and minus one. So the first thing to convert that into binary. So our quotient digits that we had was minus 1 1 minus 1 1. So the first thing that you can do is replace all those minus ones with zeros. Okay, then shift them left. So we are going to do two things over here: shift them left by 1. Okay, complement the MSB. So if it is 0, this becomes 1. And since you are going to shift it left, you have this vacant place over here. This is going to get 1, always a 1 over here. So this LSB is always going to be 1. Okay, so you're going to shift it left, put a 1 over here, right? And complement the MSB. There's 3 things that you're doing: shift left, complement MSB, put a 1 over here, right? Now this is your converted quotient. And for a correction, what you need to do additionally is to increment Q, because you subtracted D from it. So you need to add 1 more to this, and when you're going to add 1 more to this, you're going to get your answer as 11100. Okay, so this gets a little confusing if there is a correction step involved, but I'm going to just go through this once more. Now, what you could have done,
Sir,
yes,
one clarification required in your previous slide. Can
yes,
you
yes, I can do that.
uh, uh, backslide? So here's when you subtract in Q2
Yeah,
equal to 1 minus n subtract, then how this 0 triple one comes? Uh, Unable to get exactly how it comes. Double zero triple one.
you are talking about this step here.
Yeah, 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 yeah.
Yeah, so how did this come over here? Now,
Yeah.
what we have to check in every step is what is the sign of the partial remainder. Is this the same as dividend? Sorry, divisor. Is this the same as divisor or not? So if they both signs the same, then you have to subtract,
Okay.
right? So if they're both signs the same, then you have to subtract and put the quotient value as one, quotient bit as one. So here we have done subtraction. Subtraction is to add the 2's complement number to it. So this number was actually 7 minus 7, and the 2's complement of this would be 7. So you have added actually 7 with it. Uh,
Okay.
Actually, you have to subtract. So you, if you are going to subtract minus 7 from it, it's as if you have added 7 to it,
Okay, fine.
right? So
Right.
subtraction of minus 7 would be plus 7. So you have added plus 7 to it. Okay.
Okay, fine. Fine, sir. Thank you.
Okay. So yeah. So I'm going to repeat that once more. Um, Now, in our previous example, what happened was we were either putting a one or a minus one. So we were putting a minus one whenever we had a number, whenever we had an addition operation, when the signs were not matching. So we were putting minus one, and the signs were matching. We were putting one, right? The first thing that we did was converted that into zeros and ones. So the simple thing was every minus one gets a zero. Okay, you can say that, okay, why were we doing that in the initial stage? We could have put a zero over here and a zero over here. Yeah, that could be done as well. So this minus one is just for clarity. That's for explaining what actually is happening. So minus one is basically telling that you are adding, and because that's not the normal operation. The normal operation in division is subtraction, which is what's happened. This is what happens in division, that normally you subtract. But the other operation is addition, which is not the normal operation. So you are just putting a minus one over here. You could have put a zero over here. Like I said, that this is just for explanation. The hardware circuit cannot hold minus one. It's holding either a one or a zero. So you could have actually replaced that with zero. So that's not a problem. So what you should have obtained the last step should have been 0 1 0 1. Okay, so the first step is, if you do this minus 1, so you replace all those minus 1 with 0. So had you done that initially, that you wouldn't need that step over here. So you would have 0 1 0 1 in the initial case. Okay, next thing is a 3 operation case. So you shift left, toggle the MSB, put a 1 on the LSB, right? Now this is with or without correction. So you are going to do that in all the steps. Okay, so you're going to do that in all the steps. You're going to do these 3 things: shift left, complement MSB, and set LSB to 1. Shift left all of them, complement MSB. So if it's 0, it gets 1, toggle that, and put a 1 over here. Now this may be your final answer now, or this might not be your final answer. Now if you need a correction, and for correction you're looking at whether we need a correction, then this is the condition if we need a correction. So if their signs are not matching, we need a, if their signs are matching, this is your final answer. But if their signs are not matching, you need a correction. And the correction in this case is you check the sign of remainder and the divisor, and if they are both same, you subtract and increment one more to this. And this is the case that is happening over here. So we are getting the signs as same, and then in this case we are going to subtract d from the remainder, so that gets negative, so that it gets positive, and then we increment one more to this q, and then this becomes 11100. So we get an answer. But in order to, so there is a proof for that, how that is equivalent, how all of this is equivalent to the number that we are getting as quotient. I leave this uh, as an exercise for you to do. It's not a very difficult thing to go through that. So the final thing is that if you're going to toggle the MSB and put a 1 over here, and where P here represents the bits in ones and zeros, so you're going to finally see that this is equivalent to the Q, or the 2's complement number that is going to, that should have been here. So you're going to see that these two are equivalent. So if Q is in minus one ones and you replace these Q, so you can go through this yourself. Um, I used to do that in the class, but I felt that student could have done that. Should do that themselves. It's not very difficult. You can go through this yourself. So the main thing is uh, this correction step, right? And in order to do that, what we need to do is we can have an exercise at this point, and I would like you to do this exercise. So I'm going to give you two numbers, and I'm going to open this screen, okay, for you to just go through that. So so we are going to see what results are we going to get. Okay, so let's have some questions here. So I'm going to just give you one exercise. Um, okay, so let's have a value of dividend as, I'm just thinking myself, 1 1 0 1 1 0 0 1. This is my dividend, and divisor is, okay, 0 1 1 0. Okay, try it yourself. So I have opened this slide for you. This is a dividend, this is a divisor. Let's try divider. The first thing that we have to check is whether there is an overflow or not. So if there is an overflow, we're going to stop over there. Okay. Now, since these are negative numbers in overflow, our rule also changes, that we are talking about the magnitude. So we are going to talk about the magnitude of these numbers. If you consider this number and shift it left to the four bits, it would become something like 0 1 1 0 0 0 0 0. So this number should have a greater magnitude than this whole number, right? Because if you're talking about the first four bit, it was easier to do in signed numbers, but for unsigned number, but for signed numbers, it gets a little difficult because of this negative weight. So it's better if you put those extra four zeros over here, so that you talk about the magnitude of this number and the magnitude of this number, right? So what is this number? Actually, this is 64 plus 32. That would be 96. And this number here has got minus 128 plus 64, minus 64. So minus 64 plus something added to that is going to be obviously less than that number. So it has got a higher magnitude, which means that there won't be any overflow, right? So if this is minus 64, what is this thing? This is 9, and this is 9 plus 16 is going to be 25. At 25 64 minus 25, right? Minus 64 plus 25. So that would be something which is less than 696 in terms of magnitude, right? So this means this is going to go fine. It's going to get a right answer in 4 bits. So you can proceed with your division operation. So what you can do is write it over here in your first step, do a shift left, right? Do a shift left, and then check the sign. So it has got a negative sign, it has got a positive sign. So if their signs are not matching, put a -1 and add it, right? And then go for the next steps. Try to do it also. Try to do that yourself. We have some time. Let's see what result do you get. So it's better if you also compute the negative of that. So this number is in 5 bits. It would be something like something. So in 5 bits, this would be 00110, and since this is 6, so it's negative would be -6, which is going to be -8 plus 2. This would be -8 plus 2. So you need to add this number with in every step wherever there is an uh, subtraction required, and whenever there is an addition required, you need to add this number.
Sir,
Yes.
hello.
जी जी, इकबाल अजीज.
Sir, ये correction. Sir, correction step was
You can just write on the chat because your connection is breaking. I cannot hear you properly. Correction set. Okay, so you need to come to that slide, right? I'll show you the next one. Um,
So at the fourth step, I'm getting 10011. So do I need to do correction in this step?
what are you getting?
10011 s raised to the power 4.
Mm, you perhaps need to check because yeah, maybe I'm not getting that right one here.
Sir, I'm getting 00011.
Triple zero double.
Yeah. Yes, sir. Same here. We are getting 00011 in S4. 00011.
Triple zero double
Yes,
one.
sir. I'm getting 00011.
Okay, so I'm going to go to that correction slide, and then we are going to see what is the right answer. So that Z here is what this number is it's actually minus 64 plus 9 plus 9 plus 16 25. So minus 64 plus 25, that would be 9 here, 13 39 here, right? And we are dividing 39 with 6. So we should get 6 and 3 as input, output. Right. So I'm going to go to the correction step now. Correction slide. So this is your correction slide. Okay.
Oh. Shift left.
Complement the MSB.
Yes. So have you people done that?
Yes, sir.
Okay. Fahad Khan. So
Yes, sir.
what is the remainder before the correction?
So the remainder before the correction is 0001.
0001 or 00011.
Yeah, 000. Oh, sorry, 00011.
Yeah, that's the right one. 0001. Then you need a correction, and when you do a correction, you actually subtract a value of d from it to get it negative, because the result is positive, the remainder is positive, and dividend is negative. So you need a correction over here.
Yes, sir.
So when you did the correction, what was your answer of the remainder?
Sir, sir, we have added. I have added the two's complement,
Yes, yes.
which
So
is
what?
which is a division, which is a subtraction. So the answer is 11101.
Right. So that's the right answer. So that's the right answer for the remainder. So anyone who wants
Excuse me,
to,
sir.
yes,
सर वही 0001 ही था मेरा कनेक्शन का प्रॉब्लम आ रहा है थोड़ा.
say that's right. 0001 is the uncorrected remainder, but then you need a correction, and after you subtract the value of dividend, because they both have the same sign, so dividend is positive,
Yes,
and
sir.
so if I go back, so dividend was positive and the remainder is positive. So if they both have the same sign, which is here in this step, if they both have the same sign, then what you do is you subtract. So you are going to subtract the value, and then you're going to get a remainder of. So I'm just going to write the remainder at this point. So it's 11101. Yeah, regarding the quotient, what you obtained should have been -1, 1, -1, -1.
-1. Yes, sir.
That's right. Okay.
Yes, sir.
Okay.
Yes.
So what you do is then you convert that into zeros, and then you do that operation of shift left and toggle MSB. So this, after shifting left, gets 1 because you're going to toggle it. This get 1, and this gets 0 0, and you put a 1 at the last step, right? So that's the one. And then since you have subtracted it, you have to increment the q by 1. So you add one more to this number, and so this number becomes 11010, which is actually -6, right?
Yes,
So
sir. This is the answer.
okay, so this is the right answer. So all of them, all of you who have obtained this answer and remainder as -3, that's the correct answer. So remainder is -3 and quotient is -6. So that's the right answer. So this is the remainder and this is your quotient. Okay, so um, right. So this is the right answer here. Okay, so I'm going to stop over here. Actually, I was about to start the floating point numbers in this class, but we don't have much time.
Sir, and continuity is needed because the concept are to be kept in mind at the time. So if you start this floating point, it would, I guess,
Yeah, it wouldn't be
completed.
it wouldn't be good to start it in a floating point in just 10 minutes, because yeah, it needs a little more time than 10 minutes to have introduction of floating point. So what we can do is just continue with the hardware divider of this, and you can see over here the change from in the previous case is we have, instead of an OR gate, an XOR gate, which is determining the quotient bits. So I'll again leave that as an exercise for you people to do. Instead of only having subtraction, we have an add subtract in this case, and then you can see here that we don't have a load circuit as was there in the previous case of restoring division, where this signal was also loading or not loading this register. In this case, it's always going to be loaded by that result which is computed over here. So I want you to go through this yourself as well. This is the divisor circuit, a non-restoring divider circuit. Obviously, it's converting minus zeros and ones on the fly, so you are not going to do that here. And yes, you just go through this yourself. Um, okay. I'm going to. I have also uploaded that book chapter on the classroom. So it has got the details if you want to read that as well, how this circuit is working. Okay, our next topic is floating point, but I'm going to discuss that starting from the next chapter, next lecture, which would be right after Eid. So I wish you all a very happy Eid Mubarak. So a very happy Eid, and enjoy yourself. It's it's not a very good time these days. So still, whatever you people doing and how whatever way you should remain safe, and I wish you all good health, and
Thank you.
Same to you,
Thank you,
sir.
sir.
Eid Mubarak to all of you.
Eid
Eid
Mubarak
Mubarak
to
to
you,
you
sir.
as
Also.
well, sir.
Sir, for you.
Okay,
Thanks, sir. Same to you, sir.
thank you. Allah
To you,
Hafiz.
sir.
Thank you, sir. Allah Hafiz.
Allah Hafiz, sir. Allah Hafiz.
Allah Hafiz, sir.
Thank you, sir. Allah Hafiz. Thank you so
Allah
much.
Hafiz.